graduate student with more mathematical and nerve in astrophysics. And he went to work at Berkeley with Richard Planck's team where I first met him. And now he's at Stanford working with Tommy Bell. Right? And he's worked on a broad range of topics, ranging from basically the MRI to full parameter disk, and now to basically formation of gout, formation of cosmic structure. And he's going to talk about some of his work today on basically dynamos, turbulence, and fractional.
Okay, thanks a lot, Phil. It's really nice to be here. I've never visited English-speaking Canada before, so this is an exciting time for me. I'm going to talk a little bit about a couple of things that I've worked on with Mordecai and Maclo, who's at the Museum of Natural History, recently, focusing on accretion disks, and I'll be talking mostly from the perspective of issues that we've been thinking about in protoplanetary disks, but quite a bit of what I talk about today will carry over to black hole disks, compact object, and AGN disks as well, though I won't specifically discuss any physics that's directly related to those things. So, just as a way of introduction, we know that astrophysical disks transport material towards their center. These are accretion disks. We're interested in the accretion mechanism, which, because the viscosity of the disk, the molecular viscosity of the fluid, is extraordinarily small compared to when compared with the length scales of interest, turbulence has to be a source, has to be considered in terms of getting astrophysically relevant amounts of angular momentum transport. So a few of the questions that we're interested in are, how do physical parameters, so dimensionless parameters of the system, such as the magnetic Fractional number, which has attracted a significant amount of interest recently, affect this transport? In other words, how does the angular momentum scale with these parameters, the magnetic Fractional number, the magnetic Reynolds number, and the fluid Reynolds number among them, those being the three most relevant for our purposes. And can this disk act as a dynamo? In other words, can it generate its own magnetic field? Does it need to have a magnetic field embedded in it when the disk forms? Will it form a dynamo? And how will that, in turn, affect the turbulence and thus the transport? So these are sort of the basic motivating questions that we're interested in. I should say I sort of skipped over why it's magnetohydrodynamic turbulence rather than simply turbulence in general. Basically, from what we know, of course, the accretion disks I'm talking about here are Keplerian, so their differential rotation is such that the outer parts are rotating slower than the inner parts. And this is a Rayleigh stable criterion, so it's Rayleigh's criterion for fluid disks. And so they're hydrodynamically stable. It's possible that convection in the disk, vertical convection in the disk, could transport angular momentum. It seems not to from hydrodynamic simulations. The total angular momentum transport in the case of for convection in the disk is generally thought to be either very, very small. Occasionally, depending on the parameter regime of interest there, it's possible that it could even transport angular momentum inwards rather than outwards, which does not help one accrete. So the most promising way to think about this turbulence that generates the stresses necessary for angular momentum transport is magnetohydrodynamic in origin. So the sort of main thinking in this, what sort of kicked MHD turbulence as a candidate to the forward about 20 years ago, is the discovery of the magnetorotational instability, which has three requirements. That is, first, a negative angular velocity gradient rather than a negative angular momentum gradient, weak, that is subthermal field, and a sufficiently ionized medium. The first two are easily met by astrophysical accretion disks. The third one is not in some disks, but is in others. So, and by others here, I'm not talking about individual objects, though that may also be the case. I'm talking about classes of accretion disks. So protoplanetary disks tend not to be very ionized, and that has a whole host of other problems, including where there's enough ionization for the fluid and the field to couple. So I won't be talking about that issue today, though I just should point it out. So the basic picture is very nicely summarized in this graphic, which comes from the Valdes and Hawley review paper in '98. And it's basically quite simple. If you imagine a slice, a sort of meridional slice of an accretion disk with the radius pointing to the right and the perpendicular direction up on this diagram, and you sort of put some amount of net magnetic field here, just makes the analysis simpler, in one part of it, and you perturb it, those perturbations grow. The numbers here represent times in terms of the orbital time. This is very rapid growth, right? We're talking, it's clear that it's sort of saturating into nonlinear behavior within a couple of orbits, an orbit and a half or so between the beginning and the end of this figure. So the other main point to take away from this, not shown in this figure, is that this instability does saturate in MHD turbulence. And it's possible that these instabilities could saturate in a form that simply redistributes things and ends up in a laminar state. There are a number of instabilities that do that. This is not one of them. The end point, fairly robustly shown over the intervening 20 years by any number of authors, is that it saturates in MHD turbulence. Furthermore, the MRI is well known to be a dynamo system. That is, assuming you have a certain number of ingredients in place, this here shows that, again, the time in orbits, or rotation periods or orbits, this is a buildup of a mean magnetic field, so that is one that, that's a complete volume average here, and you see that it oscillates in time. The dark line here is the toroidal component, so that is the field in the direction of rotation. The dashed line is the radial, the dotted line, sorry, is the radial field, and the dashed line is the axial field, which is identically zero, in fact, in this case, for reasons of symmetry of the simulation. But nonetheless, this is sort of so this figure comes from Brandenburg and collaboration in 1995, though there are a number of other simulations that show this behavior just as well. So one of the main points that I want to make, though, is that this is certainly true for some parameter regime. Some part of parameter space, the MRI does generate its own mean magnetic fields on the largest scales. In this case, it's a local simulation, so the fields are mean in the local box, though there have been more recent studies showing in the global disk, a model of the entire accretion disk, a simulation of the entire accretion disk, that you also get mean magnetic fields in fully global simulations as well. So one of the things, this is just sort of an aside, but it's one that I think is quite interesting. The MRI dynamo is never in the kinematic phase. So in dynamo theory, we often think about the kinematic phase and the nonlinear phase, where basically, if you imagine sort of a classical dynamo picture, you say you take some velocity flow field, whether it's self-consistent from turbulence or it's forced, and you say, well, let's forget the Lorentz force. Right? So we'll neglect the back reaction of the magnetic field, and we let the magnetic field grow exponentially as a result of the fluid driving. So that's the kinematic phase. And at some point, of course, the magnetic field grows to a strength in which that's no longer a valid approximation. You have to take the Lorentz force into account. And this sort of is the sort of nonlinear dynamo system. But one of the things that's interesting about the MRI is, in this case, the fluid motions that are driving the dynamo action are themselves generated by a magnetic instability. So they're mediated in such a way that you can't, if you turn off the Lorentz force, nothing happens. The system will be stable. So it's something of an aside, but something that's interesting to keep in mind for reasons that hopefully I'll get to in time. So the main question that we set out to answer is, how does the MRI scale with dimensionless parameters? The most important ones in this case, we have a sort of standard MHD system, so the important parameters are the Reynolds number, the ratio of advection to dissipation, the magnetic Reynolds number, the ratio of advection to magnetic dissipation or resistive diffusion, and the magnetic Prandtl number, which is the ratio between the two diffusivities. And we want to know how the angular momentum transport scales as a function of these parameters. So we're certainly not the first people to do this. There have been a large number of studies, including some by people in this room. This is sort of one of the earliest papers, and I forgot the citation. This is Martin Pessah paper from 2007, where he was analyzing older simulation results, and this is sort of a complicated figure. But here we're just sort of measuring the so-called alpha parameter, or for the purposes of this, the amount of angular momentum transport versus the ratio of the most unstable wavelength of the MRI to the box size. And so what this says is that as you sort of decrease the field strength that you start with, you end up decreasing the amount of angular momentum transport until you hit a point which is the point where your resolution of your simulation is equal to that most unstable wavelength, and at that point it saturates below that. The point being that this line here, as you change the resolution, you make the resolution smaller. Imagine extrapolating this curve downwards. You have a linear relationship between the resolution of the simulation and the amount of angular momentum transport that you get out of that simulation, which is obviously very bad, because it means that as you go to higher resolution, you increase the amount of computing power that you use, you would expect to converge to some reasonable solution, and this is telling you that exactly the opposite happens. The better your simulation, the less transport the angular momentum, less angular momentum transported by the MRI, which suggests that if you extrapolate this all the way down to, let's say, reality or some reasonable approximation of reality, the MRI transports no angular momentum in any astrophysically relevant quantities. So this sort of was formalized into a slightly more physical argument, rather than sort of relying on saying, hey, which is, if you recast these, all of these simulations, I should just say, that they're analyzing, did not include explicit terms in the equations model for resistive dissipation and viscous dissipation. So they were relying only on numerical resistivity, numerical viscosity to stabilize the system and to dissipate the energy.
So the magnetic Prandtl number was about 1.
Magnetic Prandtl was about 1, roughly speaking. Though that's tricky. It's tricky to say that. It depends on the scheme used. It depends on the resolution. But that was the sort of idea, is that it's 1.
Why does anybody ever think you can get away with that?
Well, there are a couple of schools of thought with that. One is go ahead.
No, never mind. Please go ahead.
It's worth discussing. I think it's better to discuss it now. There's one school of thought which says that as you move to some high Reynolds number, anything is an approximation. And if you have a situation where you're basically never going to be in a Reynolds number that's relevant for your study. So the point, I think, the general philosophy is if you don't include those terms, assuming that the grid dissipation acts in some reasonable way, that is to say there's no large nonlinear mode coupling between the small grid scales and the larger scales of the box, which is reasonable, at least in some instances. I don't think it is for the MRI in particular, but in general, especially for some fluid systems, you look at the power spectrum, you look at the nonlinear mode coupling between small scales and large scales, and you see that it's relatively small, especially for hydrodynamic turbulence. Then that's the sort of motivation for just getting rid of that altogether. Now, whether or not you think that that's a reasonable thing is not an argument I'm personally going to make, because I generally have gotten away from doing that myself. But there are very smart people who would argue that, and I think there are reasonable things. Maybe we can talk about that a little more later. But it's a good point. So one of the ways you could reformulate this problem is you say, well, okay, what if we start thinking about exactly that? Is the Prandtl number 1 when you have grid dissipation? So there's a resistive dissipation from a simulation exactly equal or is roughly equal to the same viscous dissipation on the same grid. And so one way to think about that is to forget about trying to study the properties of your numerical scheme and just put in physical terms that represent viscosity and resistivity. And so one of the first studies to do that was Sebastian Frohman and collaborators at Cambridge, where they basically put in these two things. So here we have the magnetic Prandtl number, and this is the fluid Reynolds number. And so the idea here is yes and no simply represent, is there transport, yes, no. So do the simulation show sustained angular momentum transport? They didn't even go to the point of trying to measure how much the transport scales, which is one of these things. They just wanted to know, is it turbulent, yes or no? And so these are quite high Prandtl numbers, well, roughly speaking. Prandtl number order 10 going down to about unity, and as they increase the Reynolds number, the fluid Reynolds number, moving to the right. So just as an aside, protoplanetary disks, which is how I sort of got interested in this, are out at the regime where basically the Reynolds numbers are enormous, order 10 to the 16, but the Prandtl numbers are tiny, order 10 to the minus 8. So we'd be somewhere down over there on this graph. But one of the things that you think of is as you go to higher and higher Reynolds number, it starts to become difficult for them to sustain any transport when the Fresnel number gets smaller. So for any disk where the Fresnel number is less than unity, which is actually most accretion disks, it seems to suggest that maybe there's a problem here. Okay, so this puzzle has been discussed by many authors beyond these. Lazur and Longaretti did another paper on this, very recent, contemporary with this one, and a number of other authors have looked at this as well. This is the same data plotted in a different space. So with all of those simulations, both these and these, neglected vertical stratification. So they considered the simplest system that hosts the MRI, and of course it's always reasonable to start thinking about the simplest system that hosts the general, that hosts the facility, the thing you want to study. So it's quite reasonable to, there were local simulations of a part of an accretion disk that neglected the vertical structure of that disk. So there's no gravity stratifying the atmosphere of the disk. So it's just, this is a cartoon, it's fairly obvious. If you don't stratify, you have a constant density above and below the disk. And with stratification, you have the gravity in an accretion disk is such that you have a Gaussian profile of density with height. So what happens when you put stratification in? And one of the most important things done by Shane Davis and his collaborators a couple of years ago is to show that the stresses converge in this. This again is the amount of angular momentum transport, roughly speaking. What it actually is the stresses, the Reynolds stress and the Maxwell stress, summed together to come up with the total amount of stress which transports angular momentum. That's actually a component of the stress tensor that transports angular momentum. And what you see here is that this is two different resolutions. The higher resolution, I think, is in black on this. Correct me if I'm wrong. I'm guessing because it ends earlier. Over a period of 150 orbits, we no longer have this problem that as you raise the resolution, the amount of stress drops. So this is converged, and that's very good. So that seems to suggest that stratification has a particularly important result. So the next question is, well, what happens with the scaling of these parameters when you have stratification? So in other words, on this sort of Froment-esque study, what would happen if you did that with stratification? And again, Davis et al. Showed some work in this direction where you have the same physical setup with different varying the Reynolds number and the Fresnel number here over some range of parameters, and you see that there's not a very clear trend here, but there are some differences. At least one of these runs dies out, and others sort of cycle at different periods. So there's a lot of interesting things here. So one of the things that we wanted to do was sort of fill out this phase space here. That is, looking at Reynolds numbers, Fresnel numbers, trying to quantify how the stratified MRI transports angular momentum as a function of these values. So our approach is, I guess at this point, I sort of have given it away. We did a bunch of simulations using the pencil code, which is a higher order finite difference code, which is available at this URL for inspection, playing, whatever. This is an image from one of our simulations showing the magnetic energy. Again, this is so here is this is the y direction, which is the direction of flow. So this is the toroidal direction. Z is the direction, the axial direction above and below the midplane. Here we have the meridional plane, the xz. So this is the radial direction and the axial direction. And this is a slice of the midplane showing the radial direction and the azimuthal direction. So there's a couple of things you can see. The things are sheared out, which is not surprising. There's a strong differential rotation or shear across this box. And the turbulence is space filling, but has a multitude of scales of interest. There are very large scale fluctuations across here and here. There are also small scale structures going all the way down to the smallest length scales we resolve in the simulation. So the problem, of course, sort of already alluded to this, is that these simulations typically are somewhere at Fresnel numbers that are roughly unity. And the astrophysical disks that we're interested in are much less than unity, 8 orders of magnitude less to maybe 2 orders of magnitude less in some of the better cases. So we have a lot of sort of work to do to be able to extrapolate these kinds of things. So these are just a brief overview, technical overview of the simulations that we did. This is sort of a cartoon of what this local approximation means. case, this is referred to as a shearing box because it's a box that we take out of the differentially rotating disk. And in here, we have a linear shear flow where we linearize the differential rotation across the side of the box, which means, of course, that the width of the box has to be quite small compared to the radial length scale over which the angular momentum changes. And so we have the x direction is radial, the y direction is toroidal, and the z direction is axial. So we were able to run our parameter space that is actually slightly increased since I typed this. The Reynolds number here, by the way, just for experts in the audience who are interested, is slightly different than other authors use. We quantify it in terms of the shear rate S, which is the dimensional shear rate. So it's in units of omega, and h is the scale height of the disk over the dissipation, flow dissipation. And similarly, with the magnetic Reynolds number just has eta here, a nu here, the viscosity replaced with the resistivity. The magnetic Reynolds number has its usual definition of the resistivity, viscosity to the resistivity. We run this somewhere between 1/4 and 4. We actually have a few that go up to 10 now, and one that goes down to 0.1. But these are roughly speaking. You clearly see that the range of parameters that we're talking about is narrow, and that's entirely limited by resolution. Here, where we run most of our simulations, or run the geometry of the box in terms of the scale height of the disk, is one scale height across in x, usually 4 and 4 in y and z. We have some that are 6 in z, some that are 8, some that are wider in radius, but the ones I'll be talking about primarily are all in this geometry.
What are the top and bottom boundary conditions?
I'll talk about that in some detail. We ran a number of different things. We have periodic boundary conditions. We have vertical field boundary conditions where the magnetic field is forced to be in the z direction, and we have perfect conductor boundary conditions where the magnetic field is forced to be tangential to the z boundary. So, and we'll talk about those different cases in a bit.
You fix the shear rate being minus 3,000 mega.
Yes, that's right. The shear rate is always minus 3,000 mega here. That's right.
And your highest Reynolds numbers is the sort of numerical dissipation playing a significant role. I mean, is it well resolved?
It's well resolved with 128 zones per scale height case, and we actually have one that we ran for a slight bit at 256 zones per scale height. It's marginal at some of the highest. We actually have a couple that are some of the high Reynolds number. Some of the ones where the magnetic Reynolds number runs to be quite high. It's starting to play a role, and I would not claim that these are absolutely in all cases. Some of the most extreme ones have some role but it's not dominant in any of these cases. So we ran a lot of simulations. This is not to say anything other than we ran a lot of simulations. So this is all the ones that are in the paper. There's a bunch more. This just gives a picture looking at sort of the effect of Fractional number here. This is actually not the best illustration of this, but the structures do change both with Fractional number and with time. This is the y component, the toroidal component, which is what generally grows to a mean field in this case. So one of the things that we find, and that others have found also, is that the MRI does continue to be a vigorous dynamo in the parameter regimes that we were interested in here. So this is the magnetic energy now. These plots are sort of space-time diagrams. So this is the z direction integrated in x and y. Height above the disk here as a function of time. This is magnetic energy here in the contours. So there are propagating spatial patterns that operate over different time scales. There are these buoyantly rising. Well, they're actually not buoyant at the midplane. Something that I won't talk too much about, but they rise up into the disk that you can see, and then there are also larger fluctuations on longer time scales as well as smaller things, which I won't talk too much about.
What sort of field geometry do you start with?
These are all zero net fields, so they're all in the z direction with some cosine.
Large scale?
What's that?
Primarily large scale.
Yes, that's right. Though we varied that a bit. They're typically large, so low k, so that the net flux is 0.
Are you going to show more of these, or is this the only case that's long?
There's one more, but
Okay, well, I think, do you tend to see things that are even above the midplane or sort of odd above the midplane?
both. And in fact, and that's a function of boundary conditions.
Okay.
that's actually not something that I was going to talk about, but since you mentioned it, the evenness and oddness is when we have vertical field boundary conditions and periodic boundary conditions, we see even about the midplane. When we use the perfect conductor, it becomes odd about the midplane. It's very strong and it persists throughout most of the simulation with no flip, as long as we've run it. So this is actually quite interesting because there are a number of sort of linear, or not linear, one-dimensional eigenmode solutions to these various dynamo regimes, which suggests that it should be the case, that the polarity should switch depending on the boundary conditions. And we find very good qualitative agreement with those models.
Are you able to run these long enough to have the initial large scale field decay?
So our initial large scale field gets lost almost immediately in the linear phase because it's zero net flux, so it actually gets erased almost by this point. There's no trace of the original field left.
Is that because of turbulence, or is that because it's running for diffusion under that field?
Both. But the turbulent diffusion dominates, so it gets eaten quite quickly. So this is, if you lower the magnetic Prandtl number, you start to see that you still generate magnetic energy, and in fact, here, this is the same scale as the previous one, which is partly why this is so saturated. There's actually, if I allowed this to be varied a little more, you'd see some of these structures a little clearer, but I wanted to make this point that you obviously make quite a bit less magnetic energy in this case, but the more interesting thing is that it becomes highly structured about the midplane. It can be different in the different hemispheres. It's also very intermittent in time, switching on and off. It becomes laminar for a while until it and then returbulent, becomes turbulent again. But there are still these sort of things. So here, when the Prandtl number is less than 1, we typically tend to find that the turbulence becomes sort of bursty or intermittent, as well as simply being decreased in strength. So let me just switch gears briefly and talk a little bit about some constraints on the dynamo action, and these are sort of generic constraints, so they're actually quite interesting. Magnetic helicity, which is sort of a linkage of magnetic field lines, a measure of the linkage of magnetic field lines, defined as a volume average, which is somewhat important here, of the magnetic vector potential diode with the magnetic field itself. You can sort of think of this by analogy with the fluid helicity, where you have the dot product of the rotation with the field, with the velocity itself, with the vorticity and the velocity to create fluid helicity. The magnetic helicity H is defined this way. This is not exactly a perfect analogy, because the perfect analogy with magnetic helicity, or with the magnetic case, is actually what we call the current helicity, because J is the rotation of B. So one of the things to note, of course, because this depends on the vector potential, this quantity is gauge dependent, whereas the current helicity is gauge independent. And so the evolution for this quantity here, the volume average of the magnetic helicity, is given here. The details aren't terribly important. The point, though, is that there's a resistive term, which evolves on a resistive time, and explicitly includes the resistivity, times the current helicity. This term is always gauge independent, so it's always physically meaningful, which means that it's interesting. However, it's very slow, right? So if you had to let the magnetic helicity change over time, if you wanted the magnetic helicity to change, you have to wait a resistive time, unless this boundary term is non-zero. So this is just a surface integral over the surface of the box. Of course, it explicitly depends on the gauge here. In terms of this is the gauge here. And this term would be 0 for our setup if the z boundaries are periodic. If you have periodic boundary conditions, then the helicity evolution must be resistively limited, which means that any large-scale changes in the field would have to evolve on a resistive time scale, which is not what we see in the simulations. And so there's something there that is worth looking into. The other thing that's interesting about it is that when you do allow this term, you then have the case that your actual helicity that you measure in your box is not gauge dependent. It's not gauge independent itself. So if you have these surface boundary terms, then you have issues of actually being able to quantify a physically meaningful result. But this equation is a robust invariant, ideal invariant, that is when there's no resistivity, it is invariant, of the field, and so it places a relatively strong constraint on the evolution of the field, and so it's interesting to think in these terms. So one of the things we did is run one of these simulations here and track the magnetic helicity. This is the blue curve here, and the current helicity, which is the resistive component of it. So for periodic boundary conditions, this red term here should be the only part that contributes to the total magnetic helicity evolution. And so what we have here, the black line, this is actually a bunch of green triangles, but I plotted so many of them that you can't actually see them as independent. The green is simply a forward Euler integration of this red term. And you see that sampled whenever these codes was output. So, whenever this was output. So it's a very crude numerical integration of this term. And you see that it overlies with a pretty reasonable degree of accuracy the magnetic helicity in the simulation. So the main point here of this is that although our code does not conserve magnetic helicity by construction, as a matter of fact, it doesn't conserve anything by construction, it does nevertheless do a fairly good job of conserving the overall magnetic helicity in a case where nothing can escape through the boundary. So this is good. So then we turn to a case where the boundary conditions are open. The question here being, would the same thing happen? In other words, are the boundary terms, the ejection of magnetic helicity out of the domain, a significant, does that happen in an MRI turbulent flow, or does it not? Because it doesn't necessarily have to. But here, it's quite clear that it does. It's the exact same thing again. The blue is the magnetic helicity measured in our simulation. The red is the current helicity. And the green or black line is an integration, a very simple integration of the current helicity term. And here, clearly, it doesn't track at all from right after the nonlinear phase of the instability. So I should just say that it's worth repeating from that graphic in the earlier in many slides back, that the MRI becomes nonlinear within a few orbits. So you can see that as soon as it becomes nonlinear and turbulence starts to be generated, magnetic helicity appears to be ejected through the boundaries. That is, the second term of the helicity evolution equation is significant. But the net effect on the actual quantity we're very interested in here, I've represented with alpha, but again, this is the stress transporting angular momentum as a function of time here. This is now a volume average for our simulation for the same magnetic Prandtl number and Reynolds number, but with three different boundary conditions. The periodic case, which is probably the least realistic, but one of the most commonly used, so that does not allow any helicity transport across the boundaries. The perfect conductor boundary condition, which also does not allow any transport across the boundary. And the vertical field, which does. And not only allows it, in fact, does indeed promote transport in the MRI case. The net effect here is, as you can see, fairly similar. The total amount of angular momentum transport is not terribly sensitive to the choice of boundary conditions. Now, there are lots of interesting things in here, which we haven't really begun to analyze in terms of periodicity and the scales, the various time scales at which things vary. But overall, the net effect of these boundaries is rather small in the total amount of angular momentum transport.
The Prandtl number is the same for all.
Yes, these are exactly the same. The only difference is the boundary conditions.
And Prandtl number is basically greater than 1.
Yes, this particular case is 2, I believe. But it's also the same for in the low Prandtl number regime. I didn't show it. It's also the same that the boundary conditions don't make a huge amount.
But alpha is smaller.
It is smaller, but yeah. I just wanted to make a point here about the helicity conservation. So we have sort of a bit of a puzzle here, which is that the MRI is ejecting magnetic helicity across the boundary when it's allowed to, but that doesn't seem to be having a huge effect on the net transfer. And
Do you know the results are saying if you don't have stratification?
No, the results are. Let me think about that for a second. So you mean, do the boundary conditions change this behavior? Yes, very, very dramatically. In fact, there was a paper earlier last year by Capia and Corpi where they did this basically a very similar thing here. With they didn't do the perfect conductor boundary conditions, but they did periodic and vertical field boundary conditions, and they find there's a radical difference. In fact, without stratification, the vertical field boundary conditions are essentially independent of magnetic Prandtl number. But when the boundary conditions are periodic in the unstratified case, the amount of angular momentum transport as a function of the Prandtl number is a power law that's roughly Prandtl number squared. So it very, very radically transfers. And the reason for that is that in that case, all the dynamo action is small scale. There's no large mean field being built up without stratification. And so the small scale dynamo is a very strong function of Prandtl number that's known from non-shearing, non-disk contexts, just roughly. And so in that case, you have to eject magnetic helicity through the boundaries in order to build up any magnetic field at all. And so as a result, the results are completely different. So yeah, that's actually it's a very interesting point. It's one that's quite different in this case.
So would it be fair to say that the ejection of helicity is not really through the simulation boundaries, but just away from the central scale?
Yeah, that's a possibility. It's very difficult to get a handle on that because the magnetic helicity flux through any given surface is always gauge invariant. There's no way to construct a gauge. It's always gauge dependent. So there's no way to construct a helicity flux that you can measure. That's strictly speaking not true, but I haven't figured out a way to do it with shear, such that you could reasonably measure inside of the domain and get a quantity that you could then sort of work with. But that is likely to be part of it, for sure.
I'm just saying you can stratify helicity. It doesn't matter so much.
Right, exactly. So one of the issues. Let me actually that segues kind of nicely into the next point here. So this figure measures the relative helicity, the fractional helicity. So a magnetic field can be maximally helical if you construct it in such a way. You think of. I actually didn't think of a good way to explain this, but there's a maximum helicity that any given field can take on geometrically. And so you can measure the total amount of helicity as a fraction of that maximum to get a feel for how helical the field is. In this case, it's measured here. So this is just one would be maximally helical, it could be not helical at all. This is the spectrum of the helicity, the fractional helicity, as a function of scale. And one thing, the sort of main point to make here, each one of the gray lines is a snapshot in time. The black line is the average over all the gray lines. This is over a basically 20 orbit period. Not all 20 orbits are pictured here, so that it becomes very difficult to see. But the point is clear, is that there's fluctuation, but the trend is rather clear. The most important thing is that the maximum helicity that we really ever reach is sort of 50%, and that's only occasionally. The average over here, the average maximum is more like 20%. So the total fractional helicity is relatively small, and that's important because it means that the constraints placed on the evolution of the MRI and the turbulence of the disk is not actually is not very strong. The total amount of helicity is never very large at any scale, whether the small scale or the large. So the point that is relevant here is that one way in which you could conceivably operate a dynamo even with closed boundary conditions, so there's no net helicity flux, is that you could transfer helicity in such a way spectrally. Helicity, by the way, I've plotted it here on a log scale, so I've given the absolute value, but helicity is signed. So what you can do, and there are a number of dynamo models that do this in the non-shearing, non-MRI case, is you can take small scale helicity of one side, so the field is tangled in one side on a very small scale, and make a mean field that grows in response to that has the opposite helicity, so the net helicity remains small or constant. The constant is the more important point. Though that's not the case here, there is some degree of it's less helical maybe in some intermediate scale, but there's not a very strong trend where you have equal and opposite scales, helicities at different scales. Okay, so let me then get to the main point, which is what the transport looks like as a function of Prandtl number, which is sort of our, what we sort of started out being interested in. So here we have the magnetic Reynolds number along this axis and the fluid Reynolds number along this axis. So lines of constant magnetic Prandtl number are drawn as the gray lines here. And then the transport, which is the log of the stress, is plotted as the color of each point. So each simulation is a point in this domain. And one of the things that you see is that there is quite a bit of it's not easy to interpret this diagram. But one thing is fairly clear, is that these is not as easy to see on the projection as it is on the projector, as it is on the screen or in print. But basically, to the left of this line, which is somewhere around 3,000, all of these drop off quite rapidly. So these are almost all totally black, regardless of Prandtl number. But everything over here has some variation, and there's structure in this. But so the transport really falls off very rapidly below some magnetic Reynolds number. So it sort of functions as a critical magnetic Reynolds number. When you're above that number, you're able to sustain transport, which may scale with the Prandtl number in various ways, and clearly it does. Higher Prandtl number, the higher Prandtl number things tend to transport more angular momentum than the lower ones. But below that, it's all essentially turning on. So we read past this in a way that's actually considerably more enlightening. So here what we have is we've plotted separately, this is just the Prandtl number dependence of the angular momentum transport for 6 different fluid Reynolds numbers. And one of the things, the dotted line is, I believe, at 10 to the minus 2. For a very low Reynolds number, there's a pretty strong dependence, power law dependence of the transport on the Prandtl number. As you go to higher and higher Reynolds number, it starts to turn over. And by the highest regions, so this chain, a number of these points here, just as a very rough gauge of the amount of numerical dissipation. There's a couple, it's difficult to see in this projection. Unfortunately, this figure is the exact wrong aspect ratio for this display. But there are a number of these that are doubled up, which are resolution studies, and you can see pretty clearly that they line up fairly well, which is a fairly strong indication that though we have more detailed things on that later. So the thing is that this starts to fall over, and as you go to higher Reynolds number, you begin to fall over. This is an equivalent statement to saying that there's a critical magnetic Reynolds number, that as you go, as the Prandtl number gets larger, I've sort of written this out, when you're below the critical magnetic Reynolds number, you have a pretty strong steep and power law dependence on Prandtl number, and when you're above it, you don't. It begins to flatten out. So here's sort of a case in which that's occurring in the same set of runs. We actually have another point here, which I haven't managed to add to this diagram yet, where it lays right there, so it sort of begins to turn over. So we have some degree of what this looks like, which is quite interesting. So the final point that I'll make is, do disks meet this critical Reynolds number? Because all of this would be for naught if, in fact, we go and try to estimate these dimensionless parameters for the relevant density and temperature regimes that were of interest, and find that it doesn't meet these things, because that would mean that we're sort of back at the beginning. So we got a bunch of numbers. So the scale height and wow, this is slightly wrong, but that's okay. The Prandtl number, of course, depends on the viscosity and the resistivity, which we get from Balbus and Reed, 2008, which is essentially an application of Spitzer resistivity and Spitzer convectivity, some modification for accretion in this context, to get these diffusion coefficients. And Ilger and Nelson give us the relevant density and temperature and regimes for the protoplanetary disk case. These are models of thermochemical models that sort of give the chemical state of the gas. They were most interested in the ionization state, but here we take their values for rho and T to get the Reynolds number. In the protoplanetary case, in Balbus and I, we were a little more concerned with black holes, and so they give the relevant regimes for that. And so note here that the relationship between the magnetic Reynolds number and the fluid Reynolds number is given by this equation. And so here we just plot those results. So here we're showing the log of the Reynolds number in these rainbow-colored things as a function of density and temperature. The black dot sits right at sort of average Ilgner and Nelson 1 AU midplane for a protoplanetary disk, so about 500 Kelvin and a density of 10 to the minus 10 or so. And so when you combine all these things together, the Reynolds number is about 10 to the 16, and the Fresnel number is about 10 to the 8. Which, of course, if you multiply these together, gives you something on the order of 10 to the 8, which is much larger than the critical Magnetohydrodynamic number in the terms that we're using, so which is about 3,000 or so. So it seems that these disks are quite easily in the regime where the Fresnel number dependence is decoupled. Or sorry, the angular momentum transport is decoupled from the Fresnel number. These dependencies.
You're arguing that you've already reached the point where the critical magnetic Reynolds number is asymptotically independent of magnetic Reynolds number below a certain threshold.
That's right.
Okay.
That's exactly right. Yep. No, it's certainly such that it's whether or not we would say that the power law is exactly 0, and so that if you went out, we have exactly the same amount of transport that we measure in the simulations. It's not a statement I'm willing to make, but it certainly seems to be that in dividing these regimes up, we are well above. You expect to be well above the region where the dependence is strong. So let me just put up some conclusions, which basically is that the magnetic helicity conservation plays a role in MRI turbulence as it must, but it seems to be a small one, largely because the fields that are built by the MRI tend to have a low fractional helicity. And that leads in turn to effect where the boundary conditions themselves have a little net effect on the total amount of angular momentum transported. Though there's quite a bit more theoretical work that we'd like to do to sort of understand that a little bit better, including the effect of helicity segregation by scale, which we've done a little bit of, but also helicity fluxes. There are ways to construct helicity fluxes in the simulation from simulation data that could be enlightening. And for so long as the magnetic Reynolds number exceeds a critical one, the angular momentum transport seems to be independent of the Fresnel number, which suggests that, and it's such that the protoplanetary and black hole disks, which I didn't really talk about, but the numbers that are also in the paper, easily meet this criterion, which suggests that some of these scaling relations are hopefully a little bit better understood. So I'll leave there, and I hope, thank you very much.
Time for a few questions.
So step by step, can you give a picture of the physical chain of events that leads to a subcritical MRI dynamo? Essentially, the physical chain of events that leads to this non-kinematic dynamo. What's actually going on? And just say turbulence happens.
The short answer to that question is no. The longer answer is, so that's actually what I was sort of alluding to at the end, is that most of what I've presented here is largely empirical. In some sense, what happens is that I didn't talk about this a little bit, but this process is quite well modeled as a number of, there have been a number of recent papers suggesting this, including one by Jake Simon and by and Gami, where the general overall picture of the mean field that gets built up is very well described by an alpha omega dynamo scenario. So that is basically the turbulence is helical, and that helicity generates a radial field, which is then easily sheared out into.
The alpha omega dynamo process is a fundamental kinematic concept.
I'm not sure I would say that. I'm not sure I understand what you mean by that.
Yeah, you have a.
It's not fundamentally.
That neglects the Lorentz force.
It was originally derived as neglecting the Lorentz back force, but something you can make it.
Well, I know people put terms in the fundamental and they have it. Okay, so you got a number of meters.
Right. So, but the alpha effect itself. So the sort of the technical point there is that the alpha effect itself can be shut off by the Lorentz force, and this is the idea of catastrophic quenching. But I mean, there are a number of ways to construct alpha. I mean, my only point is that there are ways. So Oliver Dressel has made a model of this, which is quite successful, and seems to do this, wherein you can construct an alpha effect that takes into account the magnetic back reaction, and it has to do with the magnetic helicity.
But the fundamental non-kinematic part says that alpha is 0 if the magnetic field is zero, whereas kinematic, it says alpha is a property of flow, independent of magnetic field. And again, that's of course is alpha times B.
Sure.
So any of these things have to have alpha being leading order depending on the field. If these things are fundamentally non-kinematic. And they don't. They of course just describe them as a property of the field or flow field, which means that it's a kinematic concept.
I don't think I'm going to say anything that's going to satisfy you on that point.
Yeah. Can I ask a,
Yeah.
The flow field is, the flow field does not exist except in of the field.
It's being driven by a nonlinear
Right,
magnetic.
exactly. So in that sense, I mean, it's a very different game than the connected, alpha.
Right.
So, right, let's move on.
yeah, so how do you measure, do you make a time average in the case of the bursty turbulence? I mean, you sure you're able to capture enough of those bursts?
Yeah, I mean, so we've measured the angular momentum transport alpha as a function of over different averaging times. As we run to longer and longer times, we get a reasonable, for those low bursty cases, it sort of converges somewhere. We're sampling enough of them.
Do you understand anything about the transition into another burst?
That's something we haven't looked into in much detail, though it does. One thing that certainly seems to be playing a role is that there is a non-axisymmetric MRI building on the mean toroidal field that builds up. So basically, when you shut off, the turbulence starts to shut off, but there's still the mean field doesn't really decay. The mean field decay time is hundreds of orbits over. And so it sort of just sits there, slowly being sheared out by whatever radial field is sitting around until the point where it itself becomes becomes non-axisymmetrically MRI unstable, which then generates a new period of turbulence. One of the things that's interesting is that that doesn't necessarily have to happen at the midplane, and so that's part of why I know a little bit about it. So we got some really interesting results with things on and off the midplane. But that scenario seems to be fairly robust, and it seems to be, just talking to other people, we all sort of seem to have a similar idea of what's going on. It seems to be that.
I'm just curious about some of the conclusion.
Mm-hmm.
So if people earlier were that higher Reynolds number, but without stratification, do they have reached the same conclusion?
So that's a good question. I don't think I can say directly that that's the case, but what I have looked at, I would think the answer is no, because as you go up to higher and higher Reynolds numbers without stratification, it doesn't turn over. It remains a power law.
So something wrong with the cascading, local coupling.
No, it's just that the source of continued transport in that case has to be a small scale dynamo, because there's nothing that builds large fields without stratification except by injecting magnetic helicity from the system. And if you don't allow that to happen, then the transport is always dependent on the amount of magnetic energy you can generate. And so that is Fractional number dependent. And that's a sort of well-known physical effect. Yeah.
Well, I guess there are no more questions.